Okay, gang, good morning. Welcome back. Happy Wednesday. Before we look at our calendar, I have one quick announcement, sort of independent of our class, but there is a presentation happening at noon today that might be worth your time. Recently, a group of folks here, a group of people that work at GCC, did a survey of local employers asking them what characteristics they value most in their employees. And many of those local employers are going to come to GCC today at noon to talk about what they are looking for in their employees. So if you are at all interested in what these local employers have to say today at noon in the library. Any questions on that? Noon in the library. Okay, I'm going to check it out too, so hopefully we'll see some of you guys there. All right, next up, so today is our 34th class. Today the Rainbow Project is due, so throw it in the folder. Data was due last time. If you didn't turn it in then, and you have it now, turn it in now. Today we're going to cover something called L'Hopital's rule. This is the last day of new material. Friday is our review day for our test, which is coming up on Monday. Once you've submitted that rainbow project, which I think many of you just did, that is the last math project of the semester. There is one more project there, but that word reflection doesn't have to do with light or rainbows or anything. It's just you reflecting on the semester. So not a math project per se. Okay, so here we are on page 40. In this class, we use L'Hopital's rule to evaluate certain kinds of limits. Really brief history lesson here. I don't speak French, but all of this is one guy's name. He lived in the 17th century. We're just going to call him L'Hopital, but he had lots of names. He was a French mathematician who wrote the first European textbook on calculus, and we got that word wrote in quotation marks because he didn't actually write anything. The textbook that he wrote was lifted completely from Johann Bernoulli. He's one of the Bernoulli brothers that you might have heard of. So Bernoulli was one of the few people back in the 17th century who understood this newfangled mathematical development known as calculus. And L'Hopital was an amateur mathematician who wanted to learn this new subject, calculus. And so he paid Bernoulli to essentially tutor him, but they didn't live anywhere near each other. So Bernoulli is like just wrote up lots of stuff, essentially a book, and mailed it to L'Hopital and said, here you go, here's how you're going to learn calculus. And L'Hopital said, this is excellent. I'm going to put a cover sheet with my name on it and print it. And so that was the first official textbook on calculus. So the stuff that we're going to do today, this is kind of like a topic that's one of these one and done things. We're not going to be using this again other than on the test and on the final exam. It's a theorem that is kind of interesting, but doesn't really appear too often in the calculus curriculum. We'll see it like once or twice in Calc 2 next semester, but really it's just sort of a one-off type technique. Okay, so let's take a look at number 2. It says we're going to do these two limits in two different ways. So this is a limit as x approaches 2 of that rational function right there. Now you'll remember the first thing we do, the absolute first thing we do whenever we see a limit is what? Yeah, well, we're going to plug in, and if the denominator is 0, then maybe we got some funny work to do. But the first thing is to plug in. And so in this case, we're going to plug in x equals 2. So I'm just going to put this in parentheses here with a little arrow. Okay, so plug in x equals 2. 3 times 2 squared minus 2 minus 10 over 5 times 2 squared plus 3 times 2 minus 26. Upstairs, what is it? That's a 12 minus 2 minus 10. That's a 0. Downstairs, 5 times 4 is 20, plus 6 is 26, minus 26 is 0. And you remember when we first started talking about derivatives, we ended up with limits. Remember the limit as h approaches 0? And a lot of the limits that we talked about, in fact, every derivative limit that came up went to 0 over 0. And so we oftentimes had to do some algebraic manipulation to try to actually calculate what the limit was equal to. And some of these algebraic manipulations were like lines of calculation long. Remember this? And so L'Hopital has this rule named after him, but really it's Bernoulli's, which gives us a really nifty shortcut for finding the value of this limit. Here it is. What we are going to do is copy that limit right there. we are going to somewhat arbitrarily take a derivative of the numerator, not the quotient rule, just the numerator. What's the derivative up there? 6x minus 1, okay? Separately, we are going to take a derivative of the denominator. Again, not the quotient rule, just the denominator, 10x plus 3. No rhyme or reason to what we just did there. But surprisingly, whatever the value of this limit is exactly the same as the value of the original limit. So this is a brand new limit, and the first thing we do when we see a brand new limit is plug in. So when we plug in upstairs, 6 times 2 minus 1, downstairs, 10 times 2 plus 3, altogether, 11 over 23. That's the value of the limit. Now, there's absolutely no reason for you to believe that that's the value of the limit. So how about we do this one the old way? Because we could have done this one back in September. Do you guys remember the technique for this kind of 0 over 0 limit? What algebra thing can we do with that? We're going to factor. Factor the top, factor the bottom, and hope that what happens? That something will cancel, right? We're hoping something will cancel. So let's do this in a different color here. So this was the old way, was to factor. Okay, so 3x, so looking for two sets of parentheses here. That 3x had, the 3x squared had to come from what first terms? Had to be a 3x and x, no choice there. That minus 10, could be a 10 and a 1 with a negative somewhere, or a 5 and a 2. It turns out it's a 5 and a 2. Can anybody tell where they're supposed to go? Yeah, 5 there, 2 there. Still have to fill in the signs, but just thinking about the outer and inners, there's a 5x for the inners, a 6x for the outers. Oh, great. I just need to build a minus 1x in the middle, plus or minus on the 5. That's a plus on the 5, a minus on the 2. Good? Keep in mind, doing it the old way has already taken longer than the crazy new way. Yes? All right. And I still have to factor the bottom. So let's factor the bottom. 5x squared had to come from what and what? 5x and x. 26, there's only two choices. 1 times 26 or 2 times 13. Turns out it's 2 times 13. Can we see where we're supposed to go? We need a 3x in the middle. 13 there, 2 there. The inners gives how much? 13x, the outers, 10x. Hey, that's going to allow us to build a plus 3x in the middle. 13 is plus, 2 is minus. And then x minus 2's cancel. And now we've got a brand new limit, right? It's just 3x plus 5 over 5x plus 13. So what should we do with that? Just plug in 2. So upstairs, 3 times 2 plus 5 over 5 times what? 2 plus 13. On top, 6 and 5, 11. On the bottom, 10 and 13, 23. Yeah. What can I say? It works. We're not going to prove that it works. It's rather curious that it works. Yeah. What's that? The function has a hole at x equals 2. That's absolutely right. Lex?
So can we only use this when there's a hole at the limit?
So there are two cases where we get to use this crazy rule here. If the limit appears to go to 0 over 0, like up there in blue, that's the first thing we saw. So 0 over 0 or infinity over infinity. Those are the only two times we get to use L'Hopital's rule. Turns out there are a few other cases where we can use it, but we have to do some manipulation first. You'll see it in the activity today. But the two things that we're responsible for, 0 over 0, infinity over infinity. Okay, one little thing here, just to tell me what you've done, because this is quite a mysterious calculation where we took the derivative on the top and on the bottom. And so just to show me, hey, Ian, I'm doing L'Hopital's rule here, I want you guys to put a little LH, first two letters of L'Hopital's name, right above the equal sign. This is not standard notation, this is Ian notation. And it's just to save you from having to write, I am, doing L'Hopital's rule gives us blank. Right, just write a little LH there so I know what you're doing. Word to the wise, be sure that you first get a 0 over 0, or we'll see infinity over infinity, because if you try doing L'Hopital's rule to something that isn't 0 over 0 or infinity over infinity, no one's going to stop you, but you'll get the wrong answer. So for example, if I tried to do L'Hopital's rule on this thing, what do you get for the derivative on top? 6, and on the bottom? 10, 6 over 10, is that the right answer? It is not the right answer. So you don't get to just do L'Hopital's rule anytime you feel like. It has to be one of these 0 over 0 or infinity over infinities, okay? All right, let's take a look at part B. So it's exactly the same fraction. What's the only change? X is going to infinity now instead of going to 2. Okay. All right, so let's give this a shot. Let's actually start this one by doing it the old way. The old way, well, there's a shortcut, but then there's the, the way we really should be doing it. So the shortcut, this is like an end behavior type thing. What do you notice about the degree on top and the bottom? That is the highest power of x on top and bottom. They're equal. And if x is going to infinity, then subtracting 10 from that massive stuff hardly makes any difference. And even subtracting x hardly makes any difference because like a million squared dwarfs the subtract a million that might be sitting there, right? So in my mind, I can just kind of cross those guys off. So it's really just a 3x squared and then some insignificant stuff after that. How about the bottom? What is it really? It's really just 5x squared and then some insignificant stuff. And so what does that limit equal to when you cancel the x squareds? This 3/5 or 0.6. Okay, so that's the short way, 3/5, just by kind of like thinking about stuff being insignificant. But that's fairly wishy-washy to just say we can ignore the -10 and we can ignore -x. So really, if we're doing it the old way, we should do something like this. I am going to factor x squared out of everything on the top. What's left in the first term? 3 minus. Okay, there wasn't really an x squared in the next term. So I have to put something so that when I multiply the x squared times this something, I still get the -x. What am I putting here? 1 over x is good. Right, we multiply those two guys to get the -x. That -10, not only did it not have an x squared, it didn't even have an x in it. 10 over x squared. Do we buy that? It might not be something you've done before, but you should believe it, because if you distribute, you get right back to where we started. So just to make sure you understand that, do the denominator as well. Go ahead and do that right now. Factor x squared out of all 3 terms in the denominator. What do we get? 5 there. 3 over x. Good. Okay. Not clear why we did it, but it's legal, right? It's reasonable what we just did. Okay, what can we do with the x squareds? And cancel them. Okay, that's great. And now we're going to send x to infinity. If I send x to infinity, skip the 3 for a second, but 1 over x, what happens to that fraction when x gets really big? Towards what number? That one goes to 0, right? Still x going to infinity. What about this 10 over x squared? It goes to like 0, even more, right? Okay, and on the bottom, 3 over x goes to 0, and 26 over x squared really goes to 0. And the only things left don't have any x's in them. So what is this limit equal to? 3 over 5, right? 3 minus nothing over 5 minus nothing minus nothing. right? 3/5. So that's really what we should be doing instead of just saying ignore everything except the leading term. I mean, you can see the 3/5 in the original problem, right? 3x squared, 5x squared. And that's where the 3/5 comes from. But really, this is the way to justify that we can ignore everything except for the leading terms. Okay, so this is the old way. But the new way involves, as we did before, just taking a look at what happens. What does the top approach when x goes to infinity? The top approaches infinity, right? I mean, imagine the top is just an upwards parabola. As x goes to infinity, you're running to the right, the parabola goes up. So this approaches infinity on the top, and on the bottom, it's another parabola opening upwards. It's an infinity on the bottom. Now, infinity over infinity doesn't equal 1. It could, but it actually could equal any number of things. So we just have to do more work. That's what infinity over infinity tells us, is do more work. But L'Hopital's rule is the allowable work now. So let's try L'Hopital's rule here. So I'm going to put an equals. I'm going to put a little LH there. It says we are doing L'Hopital's rule. Derivative upstairs and the derivative downstairs. Do not use the quotient rule. Completely separate. What's the derivative upstairs? 6x minus 1. Let's keep that limit in the front. We'll need it. 6x minus 1. Downstairs, 10x plus 3. Okay, we're sending x to infinity. What happens upstairs? Six times infinity minus 1. Infinity. Downstairs? Infinity. What do you think we're going to do? Another derivative, because infinity over infinity is one of the times we can do this crazy new rule. So equals with a little LH on top. Copy your limit. And then not the quotient rule, but separate derivatives upstairs and down. Upstairs, 6. Downstairs, 10. Now it's constant. We don't care about x going to infinity. What is this limit equal to now? 6/10, which is 3/5. That's about the right reaction there. Okay, so to summarize, it's here number 3. The above technique works for general limits of indeterminate form of type 0 over 0 or infinity over infinity, and they could have been minus infinities in any order, doesn't matter. So indeterminate form just means 0 over 0 or infinity over infinity. Indeterminate, not determined. You can't just look at it and know. Yeah, Levi. Yes, any combination of infinities. All right, this technique is called L'Hopital's rule. The things that are written here, A and B, just say you get to take a derivative of f on top and a derivative of g on the bottom, and just that's a brand new limit, and it's equal to the original limit. All right, so that's just the kind of more formal write-up of the theorem. Real quick story here, and then we'll do the activity on the next page. When I was in grad school, we did like a little teacher training, because almost everybody in grad school like becomes a teaching assistant, a TA, and like runs like homework recitation sections, and then sometimes eventually teaches their own class. And so in this little orientation, kind of like teaching these like hardcore math students, like, hey, here's how you become a teacher. We had to like do a little sample teaching demo for the other people in the orientation and the person leading the orientation. And the topic that one of my peers did was L'Hopital's rule. He was teaching L'Hopital's rule to like a Calculus 1 class. And he had this great line, which I'll never forget. He had an example that we had to do it twice, right? We had to do L'Hopital's rule twice here. And so like we did L'Hopital's rule the first time, and then he gets here and he says, oh, and this is another indeterminate form. And so he says, in the immortal words of the Eagles, take it to the limit one more time. Yeah, we got it. We got it. All right. Okay, on the next page, the activity begins. There are far too many examples in number 1, so I want you to selectively do these ones right here. Everybody make a note of this at the top. You are going to do 1, parts A, B, D, G, J, L, and M. 1, A, B, D, G, J, L, M. Once you finish M, and you continue on the rest of the activity, which is number 2 and number 3 and number 4. You just go all the way through the rest of the activity, okay? If you finish everything, come back and do the ones you skipped. I will walk around.